finally, the question comes, you have to find some suitable avenues where you will be getting through with added interest into it. Anyhow, let me share my screen for the uh, today's presentation. Divya, is it visible? Hello.
Yes, sir, it is visible.
Okay. Okay. So I'll be briefly introducing what is this subject, graph theory, and later I'll be discussing some of its beautiful applications. So graph theory, introduction and various applications. This is what the title goes. This is how I proceed in my talk. Outline of the talk is given here. I'll be giving some important definitions in graph theory because for the fifth semester students, this subject is a newly introduced subject. Therefore, I have to uh, give some time for describing the terminologies first. Then some important theorems will be mentioned. Proof will not be dealt with. Then after that, I'll have to deal with some applications, as I said. Then to just give you, because knowledge, if you get, it should be added with your own contribution later. So research is an unavoidable thing in any student's career. So some areas of research also will be dealt with. Now, finally, I'll give you some good books for reference for beginners. Okay, graph theory, it is originally introduced in a paper by Leonhard Euler describing a problem known as Kronisberg bridge problem. This is the figure corresponding to that problem. There are 7 bridges and under which a river is flowing. Prussia, or now in Russia, that's the place is known. See, before that, let me tell you, almost all the problems in graph theory start with simple puzzles. And this is a puzzle which was then uh, uh, famous in that period when Euler attempted it. Many were trying to crack this puzzle. The problem is this one. See, look at the second figure in which these 7 bridges are rightly visible. The question is, it is connecting 4 land areas, one land area here, second land area here, third one here, and fourth one here. These 4 land areas are connected by these 7 bridges. The question is, can a person start from a bridge, start from a land rather, cross over all the bridges exactly once and come back to the place where he started? This is a question. You can visit places repeatedly, but you cannot cross a bridge more than once, but you must exactly pass over the bridge at least once also. So what Euler did was to convert that problem into this kind of a figure. There comes the uh, historical beginning of graph theory. See, these are the 4 land areas, and these lines, later we call it as edges, as the connecting bridges. Euler proved that this problem has no solution. Fantastic. For a problem Sometimes there may be solution, and saying that nobody has to attempt this problem for a solution is again another interesting thing. So Euler answered it in negative, that this problem has no solution. So later, an area in graph theory called as Eulerian graphs have been introduced in his name. Okay, let me move on. So this is another puzzle uh, introduced by Hamilton. So Hamilton gave us 20 cities. These are 20 cities. The question is, can a person start from a vertex or start from a city, move around and visit all the cities exactly once and come back to the original? So this is the solution. Here is the solution. For the previous one, there is no solution. For this one, there is a solution. You can start from here, move here, reach here, reach here, then move, move on. Then you are visiting all the places and you are coming back. So this is what we call as Hamiltonian cycle. There is a chapter in your syllabus to learn about Eulerian graphs and Hamiltonian graphs that you will learn in a separate chapter later. I will not be dealing with such things in a detailed manner because this 1 hour I will not be able to touch upon all such things. Anyhow, just to emphasize the fact that simple problems will give rise to a branch which is applied for, see, almost 280 years gone after the invention of graph theory. But after that, you see several researches are taking place, and still it is a topic which is hectically researched on. Okay, so these are some examples of graphs. This is what we have. It is clustered social networks. Social networks you might have seen. For example, Facebook is an example of a social network, Twitter, WhatsApp, whatever it is. So these are groups which are clustered having some similar properties. So huge network of people having some relationships is what we analyze in social networks, and it is abbreviated as SMA. And my research is on certain social networks using spectral theory. So that's, I want to make a reference, passing reference to it now. So this is an example of a graph. Okay, this is a small picture of a very big network. It's called what we called as internet. Without internet, new generation cannot live, or we cannot live. So a network of networks is what we call as internet. Computers, servers, many other things, mobiles are connected together by, see, it's actually a random network. This is an area where research is going on. Random networks means all the times connections will be there. There will be connections and actively involved gadgets only depending upon time. So this is what we call as random networks and random graphs. So random graphs is a new topic where research is going on. Okay, this is what I have mentioned: Google services, Yahoo, Facebook, Bingo, whatever it is. So all you see, actually, we are living in a connected world. So if you have some objects and if you have some connections, there comes graph theory. If you want to learn objects and the relationships, connections between them or disconnections, how far they are connected, measuring the connectivity, and all are dealt in graph theory. Okay, for learning any language or for learning any subject, we require definitions as well as basic theorems and results. By the by, I have to pause for a moment. Actually, a mathematical technique or mathematical subjects are based on axiomatic setup. So we'll have some definitions based on which we'll derive certain results. So axiomatic theory is in the modern mathematics or higher mathematics requires thorough knowledge of set theory. So set theory and related concepts like relations and functions are very essential for advanced mathematics. Just like numbers do a major role in school mathematics or arithmetic, in advanced mathematics, you cannot learn anything except having a sound knowledge in set theory. So sound knowledge of set theory, relations and functions must be your first aim to gather it, to assimilate it if you want to excel in higher mathematics. Okay, so first of all, let us define what are graphs, mathematical definition of graphs. We require a non-empty set V. This is the first requirement. Non-empty set V must be there. The elements of that non-empty set is what we call it as vertices, or single element is a vertex. Then the second thing which we require is set of edges. This is edge set, and each element in that set is called edge. So this E, the set E, must be disjoint with the set V. So actually, this will be a subset of two element subsets of V. Means you take two elements, see, you can have many two element subsets of V. That will be so let me call it as 2 raised to V if I denote it like this. So the edge set will be a two element subset of V. Then more than that, I should have a very important thing. That is what very important, an incidence relation. Incidence relation means how this edge E is related to a vertex V. That means Ig of E is equal to V. So instance relation on it's a relation from E to two element subsets of V. Okay, so but as we are dealing with symbol graphs means for okay, before that let me give you one more definition, then it will be clearer. So this is graph. Then after that, if you have a, so now many times we'll be drawing pictures to represent graphs. So these are the vertices. Here, let me make it as V1, this is V2, this is V3, this is V4. So from V1 to V2, suppose there is an edge. Then V1 to V3, there is an edge. That means if I call this as E1, IG E1 is set V1, V2. So this two element subset is related with the edge E1. This V1 is called one end vertex of E1, and V2 is another end vertex of E1. Okay. Now, as far as this edge E2, second edge, is having one end vertex as V1, the other end vertex as V3. It goes like that. Okay, let me give one more figure. In the previous Konigsberg bridge problem, the figure was like this. There are two bed bridges here. So let me call it as A, B, C, D. So the land areas are A, B, C, and D. Now let us see AB is the edge E1, say E1. Then the edge, another edge is there, E2. So here A and B act as the end vertices of two edges. Therefore, these two edges are called parallel edges. So parallel edges are those edges whose end vertices are the same. So here there are two other parallel edges. This is what we call a straight edge or a simple edge. So AC, simply we'll be writing it as AC. AC is also an edge, a simple edge. Now this one BC is another edge, DC is another edge. So totally how many edges? 1, 2, 3, plus 2 5 plus 2 7 edges. That means 7 bridges were there. So those 7 bridges are represented as edges. So this is the figure for that. So this is what we called as a graph, which is not simple because there are parallel edges. More than that, sometimes there may be something like this. This is what we call as, let me draw it another way. Suppose we have a figure like this. Say A, B, C, and here is something like this. This is what we call it as a loop. That means for this loop, say if I denote E, its one end vertex is B and the second one vertex is also B. That means IGE is equal to BB. So repetition is there. So anyhow, it is multi-set, we call it as elements can be repeated. So here loops are there. But in many problems, we'll be dealing with graphs without having loops and parallel edges. Such graphs are called simple graphs. So what are simple graphs? Simple graphs are graphs without having loops and multiple edges. So now onwards, from now onwards, unless otherwise stated, I will be dealing with simple graphs. Okay. Now, another important thing which you have to remember is what we call it as degree of a vertex. Degree of a vertex. If you have a vertex or a graph rather, let us call it as X, Y, Z, and V. Let me draw it like this. So here, degree of a vertex, degree of the vertex V, it is denoted by D of V, is nothing but the number of edges incident with that vertex. Means how many edges are incident with that vertex. That means here is an edge with other ender vertex as X. Here is another edge starting with we cannot say starting, having incidence with V, but the other end vertex is Z. Then this one is another edge having another end vertex Y. So totally there are 3 edges incident at V. This is the terminology we use, incident at V. So degree of the vertex V is 3. Whatever degree of the vertex X, it is 2. And degree of the vertex Y is 3, and degree of the vertex Z is 2. So it goes there. So degree is an important aspect in graph theory. Using that, if you know this, we can have the first theorem of graph theory. First theorem of graph theory. It's also known as handshaking lemma. It is first proved by Euler. It goes like this. If you take a graph, for the time being, let me have, it is even true for non-symbol graphs, means graphs having loops and multiple edges. But let me have a graph G with vertex set V and edge set E. Suppose there are n vertices and m edges. Usually this is how in literature we will denote it as, this one is called the number of vertices, that n is what we call as order of the graph, and number of edges, if we denote it by m, that's what we call as size. So if we have a graph, with n vertices and m edges, and we denote degree of the vertex like this, we just add all the degrees of the vertices. Means what you choose any v from the vertex set, calculate its degree v, choose another vertex, going on adding, you see this will be nothing but twice the number of edges. So this is a very beautiful theorem known as first theorem of graph theory. And it has a nice corollary, very important corollary. That means in any graph, you should have even number of odd vertices. That means, how do you say that a vertex is odd? A vertex is odd if its degree is odd. If d of v is odd, that v is what we call it as, this v will become an odd vertex. So in any graph, the result says that in any graph, you can find only even number of odd vertices. Proof you might have learned. Anyhow, that's an important corollary of first theorem of graph theory. Then the actual study of graph theory starts with the definition of walk. This is very important. Walk, I'll write it, these three things: walk, then trail. Trail, will be dealing with trail in the chapter on Euler graphs. Then the associated terminology path, and the last one cycle. So these are the building blocks of graph theory. Unless you learn these four definitions clearly, you cannot learn graph theory in its entirety. So let me treat each one of them one by one. So what is a walk? Walk in a graph. Walk in a graph means you must be given a graph G. For the time being, let me take it as a simple graph. Instance relation is not that much important in a simple graph because there is no loop, there is no parallels. So simply we'll be writing it as a simple graph like this. Walk is nothing but a sequence of vertices, alternating sequence of vertices. So you should start with a vertex. Let us denote it by, so usually a walk is W colon V1, then followed by an edge. For that edge, this must be an end vertex, then another vertex, then this V2 must be an end vertex of E1, then follows edge, let me call it as E2, then comes another vertex. For that, this has one end vertex as V2, another end vertex as V3, goes like that. Suppose last but one edge is some EK, it stops at V, this must be, okay, Vk plus 1, because for 2 it is 1, for 1 it is 2, then for 3 it is 2, like that. So, and so this is V1 ending at, so it's a we say that it is a V1 Vk plus 1 walk, or if I usually a hyphen is V1 Vk plus 1 walk. So W is a V1 Vk plus 1. So it starts with V1. Next must be an edge having one end vertex as V1, and you will be having another vertex that will be another vertex of this in between edge E1, like that it goes. So walk is a beginning terminology in learning how connected a graph is. So after that, when you learn walk, immediately next definition comes, which is that of trail. Trail is a walk. So you must learn what is trail is a walk where no edge is repeated. No edge is repeated. That means in that walk, if nowhere an edge is repeated, such a walk is what we call as a trail. But I will be concentrating on to the next definition, namely path. This is very important. Path is a very important object in graph theory. Path is that walk where no vertex is repeated. Previously for trail, no edge is repeated. Here, no vertex is repeated. If no vertex is repeated, automatically no edge also will be repeated. Therefore, let me give an example of a graph and show you what is a path in that. Okay, this is my graph. There are 5 vertices. That order of this graph is 5. Let me have like this. Okay, how many edges? 1, 2, 3, 4, 5, 6 edges and 5 vertices. Therefore, 6 is the size of the graph. So let me mark these vertices as A, B, C, D, V. Okay, let me have a walk, sorry, path first. Path starting with V. I am starting V. So I will write V. Move over this edge. Let me call it as E1. So E1 is written. Then move, or see, I have reached here at vertex A. So I have write A here. Then I can travel only along this edge. Okay, so it is moving. So let me call it as E2. So I have right here E2. Then I have reached at B. So I have started from V and I have started at B. Now, how many vertices are there? V, A, and B. Therefore, this is an example of a VB walk where all the vertices are distinct. Starting vertex, ending vertex, vertex in between, they are called internal vertices. All are distinct. So such a walk is what we call it as path. Length of a path is very important, means number of edges in it. So note down the point. Length of a path is nothing but number. Here it is 2. There are 2 edges. So this edge as well as this edge. Therefore, it's a path of length 2. After that, another important idea which you have to remember is that of a cycle. Cycle, let me have another graph, then I'll explain what is a cycle. So here also there are 5 vertices and you can count number of edges. I'm not interested in that size. Now let's start with, say, let me mark it like this. A, B, C, D, V again. Let me start with A. Move over this B. So I have traveled. Then, so I have reached A. Let me call this as edge E1. Therefore, it is E1. I have reached B. Okay, then I have to move here. This is E2. So I have, so E2, then the other end vertex should be marked. So far I have traveled from A to C. So it's an AC path, I can say. Now let me move to V by this edge. So let me call it as E3. Therefore, E3 is there. Then I have reached at V. Then I have to come back to A. That's very important as far as cycle is concerned. Therefore, call it as E4. Therefore, it is E4. I have to reach at A. So starting at A, ending at A, these are the only vertices in that cycle which are same. All the other vertices are different. So it can be simply taken as a closed path, we can say. So this one, let me mark it with another color. Starting with A, I have reached B, then move this one. So this is a cycle in this graph. You can have another cycle. Let me mark it with another. Okay, this one. Starting with A, moving over to D, then C, B, back to A. This is another cycle. So what cycles are there? So let me stop for a while here because you have learned things like walk, trail, path, and cycle. Now, let me give one more very important definition. Then that is called connected. Connected. First of all, let us define what is meant by connected vertices. After that, we'll define connected graphs. So anyhow, that means 2 vertices in a graph. Let us take them as U and V. 2 vertices are given in a graph. I will be saying that those 2 vertices are connected if there is a path connecting U and V. That means there must be a UV path starting with U and ending at V. There must be a UV path. Then we say U and V are connected. Path means if there is an edge, straight away edge, that is also a path. So if there is an edge or a path, generally there is a path, then we say such vertices are connected. A graph becomes connected. A graph becomes connected if every pair of vertices, you take any pair, you take any 2 vertices U and V, and see whether there is a path connecting them, then such graphs are called connected graphs. So connectivity problems are very important, especially in computer science and network transcommunication networks, like telecommunication networks, many other things. For example, even in our brain, there are many nerves are being tied up, connected. And so if some connectivity problems are there, we'll not be thinking properly or will not be able to do our actions properly. Anyhow, let me come to the application later. So I have defined what are connected vertices and what are connected graphs. After that, the next definition which you have to remember is that of components. So once a graph G is given, for the time being I told you it's considered as a simple graph. Suppose a simple graph is given, then this graph, if it is not connected, it will be called disconnected. Means there must be at least two vertices. So you cannot start from U and you cannot reach at B over a path. Such a path is not there. At least such two pair of vertices must be there. If such a graph is there, then it will have more than one pieces, or rather, before that, in order to define components, I have to define what are we called as subgraph. Subgraphs. Subgraphs to define, it is very simple. If you are given a graph G, a graph H is called a subgraph of G. There is no notation to write in between. We'll have to simply say H is a subgraph of G if vertex set of H is subset of vertex set of G and edge set of H is a subset of edge set of G. So if the vertex set and edge sets are correspondingly, respectively, the subsets of the edge set of the supergraph, this is a G is supergraph and H is subgraph, then we say H is a subgraph of G. Now, there are many particular subgraphs which you have to remember. That means if you have a, say, if you are given some vertex set F subset of B, or the notation in your textbook is, let me use that itself. If you have a vertex set U subset of B, this is non-empty. For every graph, the vertex set must be non-empty. That's very particularly remembered. So if we have a vertex set which is subset of B, maybe a whole set or the, then we can talk about a graph. This one is the notation. This is what we call as induced subgraphs. Induced subgraph means all those edges in the original graph G for which n vertices are there in U must be selected. So first of all, if you call it as H, if you call this as H is equal to G of U, this is the induced subgraph. What we require is V of H is nothing but U. Then the question is, what is the edge set of H? So regarding graphs, two things are very important. So basically, when a graph is given, you have to ask yourself what is its vertex set and what is its edge set. So here, edge set is those edges whose end vertices, that means if E is equal to UV, U is the one end vertex and V is another end vertex, both U comma V must be in this U. So all such edges are collected. Nothing should not be eliminated. Then we'll be getting a subgraph, which is what we call as vertex-induced subgraph. Similarly, there is something called edge-induced subgraph. That means what is to be given first? You have to be given an edge set, subset of is edge set E. Then this is the notation we call it as edge-induced subset. So what is already given? F. Then you create vertex set of, if I call it as H, then vertex set of H will be those vertices whose which become the end vertices of the edges in F. They are collected into. So vertex set to be fixed, edge set is already fixed. Such a graph is what we call as index. So actually, this is yeah, this will be the graph having edges f and vertex like this. Now, after that, uh, let me give one more example and go for the remaining part of my talk, because these are there in your textbook. But I want to emphasize these points just because of the fact that in order to learn a language, unless you know the alphabets A, B, C, D up to Z, or the preliminary words, you cannot talk, you cannot write. So these are building blocks of abstract mathematics. So let me give you a very important definition, one more definition, then I'll stop there and go to the next part of the talk. Okay. Yeah, this is very important. One is vertex removal. Then the second operation is edge removal. How this can be done in a graph? For example, suppose you consider a computer network. Here is a computer. Here there are 4 computers, 5 rather. See, I'm connecting this using, so here vertices are computers and edges are the connections. Suppose this is a server, very important main computer. Suppose it is failed, means it is not working. Therefore, there is no role of this connection and this connection, because it is not working means nothing will be passed to this computer or this computer. If this computer is not getting from the server, this will be. So anyhow, if I remove, vertex removal generally means if something is gone, some vertex is gone, corresponding edges are also gone. So that is the impact of vertex removal. But for the edge removal, if one edge is removed, that edge only will be removed, vertices will be there intact. So that's the main distinction of edge removal and vertex. So as far as a graph is concerned, the very important object is vertex, because computers are important, and the connections, even though they are important, it is inferior to the objects called vertices. Okay. Okay, so you have to remember all these things when I talk about the applications or something like that. Anyhow, let me give another structure which is also very important in graph theory. This is what we call it as something very familiar word, which is tree. So a tree is a graph. A tree is a graph which has no cycles, but it should be connected also. So a connected cycle-free graph. Cycle-free graph is often called as acyclic graph. Acyclic graphs, I'll tell you the importance of acyclic graph later, because in the present world, we are living in a digital world, and we are using digital money, cryptocurrency, bitcoins like that. In cryptocurrency coding, this acyclic graph will come. I'll refer to it later. Anyhow, tree is a graph which is acyclic, means no cycles, but it must be connected. Several characterizations you will learn in your graph theory textbook. That there are several characterizations. So another thing, a point of reference I have to make, these characterization theorems should be carefully noted. Characterization means it is something which tell you that if something is a tree, it has to satisfy some condition. If that condition is there, it must be a tree. So there's something called if and only if theorems. So such theorems, characterization theorems, is a way of looking at the same object in a different way, because you have an axiomatic definition. What is the axiomatic definition here? A tree is an acyclic connected graph, but that kind of checking whether there is a cycle, whether it is connected, is not an ASIC process. Therefore, there will be some other ways of looking at the same object called tree in a different way. Let me give you one simple characterization. That means Yeah, a connected graph G, a connected graph G with n vertices is a tree if and only if the number of edges is equal to n minus 1. So this is one characterization. So let me give you a very particular tree, which is itself called path. That's also very important as far as graph theory is concerned. Let me take this is an example of a tree. But how many vertices? 1, 2, 3, 4, 5 vertices. So for n is equal to 5. How many edges? 4 edges. So 5 vertices and 4 edges. But this is often denoted as P5. So it's an example of a path, UW path. So if such a tree is given, it is often denoted by P5. Generally, Pn denotes a path graph or simply path having n vertices and n minus 1 edges. So path is a very important, path graph is a very important object in graph theory. So another thing which is already we learned what is meant by a cycle. Suppose we have n vertices and you have only one single cycle in that. It goes like, suppose here is one vertex, two vertex, third, four, five, six. Six vertices are there. Therefore, this is what we denote it as C6. So C6 is the cycle here. Length of this cycle is number of edges in that. Therefore, there are 6 edges because this is not a tree. There is a cycle, means it's not a tree. Therefore, here m should not be equal to n minus 1. Here you can see that m is equal to n. My natural question is for the students, can you tell me this is the only possibility where you can have m is equal to n? Can you have another case? So of course, for example, if I add a vertex here, let me 7th vertex is added, then also you can see m is equal to n because there are already 6 edges here, one more edge came, therefore here also m is equal to n. Such things are called unicyclic graphs. So unicyclic graphs, if you want to do research later, unicyclic graphs are also very important. So I have mentioned some important basic definitions, and one theorem I have mentioned, that is first theorem of graph theory, and characterization of tree I have mentioned. It is one characterization. Another characterization of tree I have to mention it because it's also very important. Means a connected graph G is a tree if and only there is a unique path. There exists a unique path between any two vertices. If you and we are two vertices in that graph G, and if you can find only one unique path connecting you and we, say only connected graph, then there is only one unique path, then such graphs must be necessarily a tree. So that's another characterization of tree. Several things are there. You will be learning about bridges. In terms of bridges, you will be characterizing trees, etc. So I'll stop here because it's already 2:55. Okay, so let me move on to, yeah, this is for your advanced learning. I have to mention this because in a seminar, it is not there, as I begin with, it is not the textbook knowledge I have to supply extra. So far we have dealt with undirected graphs. In your syllabus, there is a portion to deal with directed graphs. Directed graphs means if you have a vertex, another two vertices, U and V, you will be having some relations with V in one way direction. U is related to V, but V is not related to A. So that means this kind of is what we call as arc. Instead of edge, we'll be calling it as arc. Sometimes there may be something here, backward also. So UV is an arc, VU is another arc. Okay, so direct graphs are also very important in modeling, mathematically modeling some systems. So that should be learned properly. Then this is out of your syllabus, hypergraphs. Hypergraphs are very helpful, which is the generalization of graphs and directed graphs. Then comes, there may be some weights for the edges. They are called weighted graphs. This is, of course, useful in your road networks and all that. I will be coming to it later. Then these are the areas where I have research, and this is a hard nut to crack, which requires some higher concepts called the Metroid theory. And these are the areas where I did my research. They are generalizations of this undirected graphs. They are called sine graphs. If time permits, I'll be dealing with a few examples of sine graphs also. Fuzzy graph is another area where fuzzy mathematics comes into play. Then they usually see. Recently, I have seen some papers written by one of my colleagues who is now working at NIT, dealing with what is it, illegal trafficking, drug trafficking, then other such kind of networks. So anyhow, these are some points which you have to keep in mind when you want to do some contributory work in your later life. Okay, now let me move on to some important applications. Yeah, graphs can be used to model many types of relations and process dynamics in physical, biological, social, and information systems. Many practical problems can be represented by graphs. I'll be picking some selective examples, currently important examples. Many things you can have from your textbook, but I'll be supplying you or giving you, citing some important examples of applications of graph theory. Yeah, nobody is in today's COVID world. Of course, we will be staying at home, but we are fond of traveling. While you travel, you might have used global positioning system works, Google Maps, then Yahoo Maps, to determine a route based on user settings. Means suppose you are traveling from a point A to a point B, you will be searching how long it will take, what will be the time from A for reaching A to B, shortest route, etc. For finding the cheapest. So from if you are using that air trafficking system, you will be checking what is the cheapest airfare between two destinations. The destinations are vertices and the connections are edges containing information such as distance, how long these two places are apart, then the fare, airfare or the bus fare between them. The software finds critical paths. Critical path problems are in operations such problems. Optimal route actions means optimization techniques are there in graph theory based on the user setting. Depending upon the user, they may be selecting different locations, different criteria. Depending upon their criteria, the software will tell you that this is the optimal solution. Okay, this is a figure which illustrates the what is that? What is Google Map location finding or shortest route finding picture. So there comes, see, these are vertices, and these are the roads networks or the airfare network, something like that. Okay, another area is where we'll be applying in computer using, there is a area called image processing, uh, image processing, signal processing, etc. There also you can see the graph theory comes into play. This is the image processing of brain using graph theoretic techniques. Okay, now, yeah, this is the road network. On the right side, you can see the roads in India, road map of India. This is, if you enlarge it, we'll be getting something like that. Google Map you are familiar with. Here and all, we'll be dealing with graphs, graph theoretical concepts. Yeah, of course, this is something about uh, uh, technologies. This, yeah. Telecommunication network management. See, we are using mobile networks. Networks means mobiles or other systems are connected via the, what is it, kind of what is, see, satellite systems or something like that. Some connections will be there. I told you random graphs come into play here because almost all the times we won't be getting the connections. When when two mobiles are connected, we say there is an edge. Otherwise, there is no edge. So probability of having connections are to be studied, therefore comes randomness. So random graphs, mainly Ramanujan graphs. Ramanujan's actually he dealt with number theory concepts. Number theory comes into play in random graphs. So there are things which you have to explore. These are all just for your what is that? What's the reference only? Later you can deal with those things. You just Google it, Google random graphs. You can see plenty of papers, plenty dealing with Wikipedia and all. So this is another article which I have taken from Wikipedia dealing with artificial neural networks. Now this is an era of artificial intelligence, deep learning, machine learning. These are some areas where hectic research is going on because man is often replaced by machines. Whether it is ethical or not, that question comes next. But robotics, artificial intelligence will help us a lot because in COVID, you might have seen in hospitals, robots are going to the patient's room controlled by somewhere and they are supplying medicine. So they are quite essential in our life. So for making the machines learn, we can use artificial neural networks. They are called ANN in abbreviation. So that's an area where there are many researchers going on. For learning artificial intelligence, deep learning, and machine learning, next semester you will be learning something called linear algebra. Linear algebraic techniques are very important in these areas, apart from graph theory also. Okay, robotics, as I told you, robotic control with graph networks. This is an item which I have selected from internet. So it deals with how robots are to be designed, their movements, etc. The connections from what and so how flexible the things are there. So in robotics also, we will be using graph theory. Yeah, circuit designing. Circuit designing is electronic or electrical circuit designing is an area where planar graphs, there is an important discussion in graph theory called planar graphs. So planar graphs, let me, for the time being, let me give you a simple example. That means, suppose you have a graph like this. Usually people in electronic design will mark it like this. There is a crossing here. There is a crossing here. So can we draw the same figure without a crossing? Yes. This is the way to draw that figure without a crossing. So with how to avoid crossings is the area dealt in planar graph theory. So there is another way of drawing the same figure. Let me show you that also. That will be curious enough. We suppose just draw the four things here. All of them are to be joined by a path. This is actually P4. Then join this one to this and this one to this. That is another way of drawing it. So different way of drawing the same circuit is what is analyzed in circuit designing theory. Okay, then image processing is already mentioned. Different images we have to process, and in image processing there is a stage called image segmentation. In image segmentation, we'll be using graph theoretical techniques, and that is called graph signal processing. Toolboxes are available. So that's an DSP, is a digital signal processing, as an area where computer scientists, electronic engineers are keenly interested in. Okay. Okay, this is very, very important. We are using Google. How the Google gives you the search results within fraction of a second. First of all, they are running with the help of a graph theoretic principle. Here we'll be using directed graphs. So there are two persons which have to be remembered. They have to remember. One is Larry Page and Sergey Brin. They designed an algorithm called Page Rank algorithm. It worth $25 million. Google Incorporation purchased that algorithm for searching the search techniques designed by Larry Page, and so they were at the age of 21 at that time. They were now the professors at Stanford University. They designed it and sold that algorithm to Google Incorporation, $25,000 something. You can search the web for the actual cost. Anyhow, algorithmic graph theory is another area where you can have a lot of research. So page ranking system is applied in Google search techniques. Okay. Now, let me come to chemistry, where chemistry we'll be dealing with organic chemistry rather. Alkane structures have one simple compound itself will have several isomers. The are compounds that have the same molecular formula but have different structures. In graph theory, in fact, the same isomorphic isomer only exists. Chemical properties is negligible. We will be studying only about the structure only, because in graph theory further we will discuss making it easier to count the like alkanes that I've mentioned. See, this is an example. This person is responsible for counting or enumerating isomers of the same structure, butane and also butane. Formula is same, but the structures are different. So iso means they are isomorphic. So isomorphism I forgot to mention. Anyhow, isomorphism you have to learn. Two graphs, how structurally they will be same. There will be one corresponds between the vertices and between the edges. So here C carbon and hydrogen atoms are connected in certain specific structure that gives butane. Then you see there is the same four carbon atoms, named same number of hydrogen atoms. So anyhow, there is a chemical graph theory. There is an area called chemical graph theory. So if you are strong enough in chemistry, you can do research in chemical graph theory dealing with molecular graphs. So I have dealt with part of it that I have calculated energy of some molecular graphs. So energy of graphs is an area where things are being looked at. Okay, I have already mentioned that your brain consists of many nerves. They can be called as edges, and you connect them with neural elements or brain regions. They can be called as vertices. Then you will be getting a brain network. Then you see these are the areas where doctors are interested. Then they will be learning. The experts will be learning about different properties of this brain by looking at the structure of the network. Yeah, this is very relevant. Today we are living in an age where many things are based on databases. Our information will be collected by government and they will be analyzing it. And this is the age of what we call as data analytics. So it's an area where statistics and mathematics come into play to analyze a huge amount of data. So tracking spread of coronavirus with graph data. This is a paper published by Alex Woodall, and many other papers are coming in. This is the paper published in March 12, 2020, after the spread of coronavirus. So graph data by using the research using graph databases is an area where several softwares are coming in. Easy methods are to be designed. Fast and quick algorithms are to be found out. So there also there is major scope for research, graph databases. Yeah, this is another paper, virus graph and COVID-19 pandemic, a graph theory approach. Oh, this is where economics, the application of graph theory in economics come into play. Bitcoins or blockchain data analytics, a graph theoretic perspective. I have already mentioned that now we'll not be using all the cash transactions. We'll be using digital transactions. Then we have to learn what are bitcoins and other digital money mechanisms. For these are the papers where they look at how these bitcoins are transferred via several networks and how they find out some faulty mechanisms if there is any corruption or if it is not proper, if the coding is not done. So coding theory is an area. in mathematics, cryptography for this cryptocurrency, we call it like that. So in coding theory, graph theory now has a major role to play. Many codes are available, but graph theoretic codes are recently researched in. Okay, now I will deal with some books for beginners. These are the three books I suggest for the beginners to look into. One is actually there is a book for Kannur University written by Balakrishnan and Ranganathan. That's a prescribed textbook. Apart from that, if you have these three textbooks, that will be giving you a supplementary role. First one is very simple to deal with, but you must be aware of the fact that two graph theorists will have the same definition dealt in a different way. So you must be things will be same, but some kind of slight changes will be there in definition. This is another book, Graph Theory by Clark. The first book is by Gary Chartrand and Ping Zhang, and the second one is by Clark and all. There are two others, and the third one is what we call it as Bible of Graph Theory. Is written by Frank Harari. We call it as Divya. Should I stop?
Sir. Yes, sir.
Shall I take 5 more minutes?
Yes, sir. Of course, sir.
Okay. Harari is he was no more now. Harari wrote this book on graph theory, not so simple, but for your research purpose and all, this book will be very helpful because it contains several important ideas. Proofs are not so easy to digest, but the first two books are very simple, lucidly written, of course useful for beginners. So I see many books you can have if you search in internet dealing with graph theory. But selectively, I'll suggest these two books for your reference. Now, to stop my talk, let me move on to some research areas. Chemical graph theory, as I already told you, is an area where you will be looking at molecular graphs, and energy of molecular graph is an active area where research is going on. And recently, when I wrote a paper to a journal, they have mentioned that the results in my paper can be even applied into molecular graphs. What they found out is that suppose a molecule is attached with another molecule by a bond, there edge comes a bond. Suppose molecule M1 is having a bond with M2 by this kind of bond. At present, the graph theorists or the chemical graph theorists rather are fond of how, what is the attraction? Repulsion they have not taken into consideration. Molecules will attract as well as repulse. So in order to take into account repulsive forces, sign graphs can be used for modeling. So topological descriptors using distance concept in graphs and many other topological descriptors dealing with to analyze the structure of a molecule is studied in chemical graph theory. That's an area where research is going on. Then social network analysis, terror network, this is SNA, terror network analysis, TNA, business network analysis, then so many other network analysis are being explored in today's world. Now, there are certain areas which require very practical application, just like how to schedule certain jobs to certain group of people, job scheduling, job sequencing, then warehousing problems, timetable preparation or time scheduling, air traffic scheduling, bus scheduling. All these things can be done with the help of graph theoretical concepts. This is where I want to stop now. Now, today I have seen this article written by Devashish Mukherjee, professor of NIT Calicut, director rather. It goes like this: Ishtamegala Tirichariga Maruga. That means, first of all, you have to understand who you are. Nobody knows you except you yourself better than anybody else. Therefore, this article you have to read. It says that you know your interests, you know your dislikes. Depending upon your like, you just select an area for your research or your study. You might have selected mathematics as a topic which you are very much fond of. So likewise, for your career purpose, you have to select a job where you can feel satisfied. That kind of selection is very important. Otherwise, dissatisfied mind will make huge noises when you go to an organization. Therefore, selection of your very intimate interest is very important. Now I stop here. Thank you for listening to my shorts talk. If you have any questions, I'm ready to answer if I know it.
Thank you, sir. Thank you for your inspiring talk. Participants, now is the time for interaction. Participants can ask your doubt either by typing in the chat box or by unmuting your mic. ആർക്കെങ്കിലും എന്തെങ്കിലും ചോദിക്കാനുണ്ടെങ്കിൽ സാറിനോട് ചോദിക്കാം. അൺമ്യൂട്ട് ചെയ്തിട്ട് ചോദിക്കാം, ഇല്ലെങ്കിൽ ചാറ്റ് ബോക്സിൽ എഴുതി ചോദിച്ചാലും മതി.
There is a message. Okay. Ask me. Please ask me.
Sir, actuarial science എന്ന് പറഞ്ഞൊരു PG എടുക്കാൻ actuarial science എന്നൊരു ടോപ്പിക് ഉണ്ടായിരുന്നു. മാത്സുമായിട്ട് ബന്ധപ്പെട്ടതാണെന്ന്.
എന്തായാലും എന്റെ ടോപ്പിക്കിലായിട്ട് ബന്ധമില്ല, എങ്കിലും എനിക്കറിയാവുന്ന കാര്യം ഞാൻ പറയാം. ആക്ച്വറിയൽ സയൻസ് എന്ന് പറയുന്നത് നമ്മുടെ ലൈഫ് ഇൻഷുറൻസ് ഏജൻസിക്ക് വേണ്ടിയിട്ട് ഒരാളുടെ ജീവിത കാലയളവൊക്കെ അളക്കാൻ അല്ലെങ്കിൽ എസ്റ്റിമേറ്റ് ചെയ്യാൻ ഉപയോഗിക്കുന്ന മാത്തമാറ്റിക്സിന്റെയും സ്റ്റാറ്റിസ്റ്റിക്സിന്റെയും ടൂൾസ് ഉപയോഗിച്ച് പഠിക്കുന്ന ശാസ്ത്രശാഖയാണ് ആക്ച്വറിയൽ സയൻസ് എന്ന് പറയുന്നത്. ഭാവിയിൽ അത് വളരെ കൂടുതൽ ജോലി സാധ്യതകൾ ഉള്ളതാണെന്ന് പറയുന്ന കേൾക്കുന്നു. കാരണം ഇനി നമ്മൾ ഇൻസെക്യൂർ വേൾഡിലാണ് ജീവിക്കുന്നത്. അപ്പൊ എല്ലാവരും ഇൻഷുറൻസ് മേഖലയിൽ കൂടുതൽ ഇൻവെസ്റ്റ് ചെയ്യുമെന്നും ആ ഇൻവെസ്റ്റ് ചെയ്യുന്ന സമയത്ത് അവരുടെ കാര്യങ്ങളൊക്കെ ഡാറ്റയൊക്കെ കൃത്യമായി അനലൈസ് ചെയ്യാൻ വേണ്ടിയിട്ട് ആക്ച്വറിയൽ സയന്റിസ്റ്റിന് ആവശ്യം ഉണ്ടാവും എന്നാണ് ഞാൻ എന്റെ അറിവിൽ പെട്ടത്തോളം മനസ്സിലാക്കിയത്. ഇതാണ് ഇതുമായിട്ട് എനിക്ക് പറയാനുള്ളത്.
ഓക്കേ സർ, താങ്ക് യു.
Anybody else?
സർ, ചാറ്റ് ബോക്സിൽ
Yes, please.
ഒരു ക്വസ്റ്റ്യൻ ഉണ്ട്. ഖദീജ മോൾ ചോദിച്ചിട്ടുണ്ട്, റിസർച്ച് ഏരിയാസ് ഇൻ ഫസി ഗ്രാഫ് കളറിംഗ്.
ഓക്കെ, കളറിംഗ് എന്ന് പറയുന്നത് വളരെ ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള ഏരിയ ആണ്. കളറിംഗ് ഉപയോഗിച്ചിട്ട് ഇഷ്ടംപോലെ പ്രാക്ടിക്കൽ ഇത് ചെയ്യാൻ പറ്റും. ഇപ്പോൾ നമ്മൾ സാധാരണ ഫസി മാത്തമാറ്റിക്സ് ചെയ്യുന്നത് അത് ശരിയാണോ തെറ്റാണോ എന്നുള്ള എത്തിക്കൽ ക്വസ്റ്റ്യൻസ് മാറി നിൽക്കട്ടെ. നമ്മൾ എന്താണോ ഗ്രാഫ് അല്ലെങ്കിൽ ഓർഡിനറി മാത്തമാറ്റിക്സ് ചെയ്തിരുന്നത് അത് പാരലൽ അതിനെ അനുപൂരകം എന്ന നിലയിൽ ഫസി മാത്തമാറ്റിക്സ് ചെയ്യുകയാണ് ചെയ്യുന്നത്. ഉദാഹരണത്തിന് ഫസി സെറ്റ്സ് ഡിഫൈൻ ചെയ്യുന്നത് സെറ്റിന്റെ എക്സ്റ്റൻഷൻ ആയിട്ടാണ്. എന്തായാലും ഫസി മാത്തമാറ്റിക്സ് അതിൻ്റെതായിട്ടുള്ള വളരെ വലിയ ഇമ്പോർട്ടൻസ് ഉണ്ട്. നമ്മൾ എൻ്റെ വീട്ടിൽ ഇപ്പം വർക്ക് ചെയ്യുന്ന വാഷിംഗ് മെഷീൻ എന്ന് പറഞ്ഞ ഫസി ലോജിക് ഉപയോഗിച്ചിട്ട് വർക്ക് ചെയ്യുന്നതാണ്. അതായത് എത്രമാത്രം ഡിറ്റർജന്റ് വേണം എന്നൊക്കെ കൃത്യമായിട്ട് ഒന്ന് അനലൈസ് ചെയ്ത് അതിന്റെ ഡിഗ്രി ഓഫ് റിക്വയർമെന്റ് ഒക്കെ അനലൈസ് ചെയ്ത് ചെയ്യുന്ന മെഷീൻസ് ഒക്കെ ധാരാളം ഉണ്ട്. അതുകൊണ്ട് തന്നെ ഈ കളറിംഗ് നമ്മൾ ഇപ്പോൾ ഗ്രാഫ് കളറിംഗിൽ എന്താണോ ചെയ്യുന്നത് അവിടെ രണ്ട് വെർട്ടീസസിനെ വളരെ കൃത്യമായി ഡിസ്റ്റിങ്വിഷ് ചെയ്യുന്നതാണ്. ഇപ്പൊ ഉദാഹരണത്തിന് കെമിക്കൽ ഗ്രാഫ് തിയറിയിൽ ചില മോളിക്യൂൾസ് അല്ലെങ്കിൽ ചില പിന്നെ എലമെന്റ്സ്, കെമിക്കൽ കോമ്പോസിഷൻസ് ഒരുമിച്ച് വെച്ചാൽ എക്സ്പ്ലോഡ് ചെയ്യാനൊക്കെ സാധ്യതയുണ്ട്. അപ്പോൾ അവരെയൊക്കെ സെപ്പറേറ്റ് ചെയ്യാൻ, സെഗ്രിഗേറ്റ് ചെയ്യാൻ ഉപയോഗിക്കുന്ന ടെക്നിക്സ് ആണ് ശരിക്കും പറഞ്ഞാൽ കളറിങ്. അപ്പോൾ മിനിമം നമ്പർ ഓഫ് റൂംസ് റിക്വയർഡ്, മിനിമം നമ്പർ ഓഫ് ഡിഫറെന്റ് സ്റ്റോറേജ് സ്പേസ് റിക്വയർഡ് എന്നൊക്കെ പറയുന്ന അനാലിസിസ് ആണ് സാധാരണ ഗ്രാഫ് തിയറി ചെയ്യുന്നത്. ഫസി ഗ്രാഫ്സിനെ കുറിച്ച് വേണ്ടത്ര അവഗാഹം എനിക്കില്ല. ഞാൻ 1-2 പേപ്പേഴ്സ് വായിച്ചേ ഉള്ളൂ. അതുകൊണ്ട് തന്നെ കളറിങ്ങിന്റെ പാരലൽ കോൺസെപ്റ്റ്, നമ്മൾ ഗ്രാഫില് കളറിന്റെ പാരലൽ കോൺസെപ്റ്റ് എന്താണ് എന്നുള്ളത് നോക്കിയിട്ട് അത് എത്രമാത്രം പ്രാക്ടിക്കലി ഫീസിബിൾ. കാരണം ഫസി ഗ്രാഫ് തിയറിസ്റ്റിന്റെ ജേർണലൊക്കെ വരുന്നത് ഈ പറഞ്ഞ പോലെ അപ്ലൈഡ് മേഖലയിലൊക്കെയാണ്. അപ്പൊ അവിടെ അവര് എന്തായാലും അപ്ലിക്കേഷൻസ് കൂടി ചിലപ്പം ആവശ്യപ്പെട്ടേക്കാം. അതുകൊണ്ട് അവിടെ അപ്ലിക്കേഷൻ ഉണ്ടോ എന്നുള്ളത് ഒന്ന് അനലൈസ് ചെയ്ത് വർക്ക്ഔട്ട് ചെയ്യുന്നതായിരിക്കും നന്നാവും.
വേറെ ആരെങ്കിലും? വേറെ ആരും ചോദിക്കുന്നില്ല എന്ന് തോന്നുന്നു സർ.
ഓക്കെ.
ഓക്കെ, നമുക്ക്
രണ്ട് രീതിയിൽ ഈ ചോദ്യങ്ങൾ ഇല്ലാതിരിക്കാൻ 2 കാരണങ്ങളുണ്ടാവാം. ഒന്ന്, എന്റെ ടോക്ക് അത് കൃത്യമായിട്ട് മനസ്സിലായിട്ടുണ്ടാവില്ല. മറ്റൊന്ന്, പിന്നെ എല്ലാം മനസ്സിലായിട്ടുണ്ടാവും. 2 എക്സ്ട്രീമിലായിരിക്കണം ഈ ചോദ്യങ്ങൾ ഇല്ലാതെ വരിക. ഇടയിലാണെങ്കിൽ ചോദ്യങ്ങൾ ഉണ്ടാവും. ചിലപ്പോൾ ഈ പിന്നെ ഓൺലൈൻ മോഡിൽ അങ്ങനെ ഭയപ്പെട്ടുകൊണ്ട് ചോദിക്കാതിരിക്കുന്നതാവാം. എന്തായാലും ചോദ്യങ്ങൾ ഉണ്ടായാലേ നമ്മുടെ പഠനം മുന്നോട്ട് പോകും. അപ്പൊ ചോദ്യം ചോദിക്കുക എന്നുള്ളത് ഈ സമയത്ത് എനിക്കിഷ്ടപ്പെട്ട കാര്യമാണ്. കാരണം എല്ലാത്തിനും ഉത്തരം പറയാൻ പറ്റുന്ന ഒരാൾ എന്ന നിലയല്ല, ആ ചോദ്യം എനിക്ക് പുതിയ ചിന്തകൾ നൽകും. അതുകൊണ്ട് തന്നെയാണ് ഞാൻ അതിനാവശ്യപ്പെട്ടത്.